So I'll repeat for all of you that he looked at changing the rate of frequency from 2 hertz all the way up to 30 hertz, 30 cycles per second, and with the titanium metal, and he saw a change in the mode of crack propagation when that happened. And so when we use usage rate acceleration, we can run into some unexpected complications here too. One of them is caused by the continuous usage, and that's if there's an interaction between the usage rate acceleration and the overstress acceleration lifetime testing. This is not going to be a problem if your material is mostly inert in the environment it's being tested in. However, if the material is absorbing water as it's being tested, like we discussed this morning with Ulrich's presentation, maybe you can have some water coming in slowly over time and changing the material properties, and that may change the rate at which the crack can grow through the material. And if we do non-stop testing, then we can end up with driving the crack forward before the water can come in and change the material properties. And so we propagate the crack at a different rate than it would propagate at the same stress normally. And so if you have any type of corrosion occurring with the environment, or the environment changing the material properties over time, or the environment may actually interact with some materials to heal the crack, to reduce the size of the crack, if the material is not used for a period of several hours. And by using the material continuously, you do not allow that healing to occur or the crack tip blunting to occur. So these can all be errors associated with continuous usage. Increasing the frequency can cause a problem because there will be an interaction. We almost always see an interaction between overstress acceleration and usage rate acceleration when we go to a higher frequency. However, there's an ability to model for that interaction and correct for it. The software that we use uses a new type of model called a general log linear model, and the equation looks like this. I'll remind you that the Greek letter eta stands for the characteristic lifetime, the lifetime at which 63% of the specimens have failed. And if we take logarithm of those lifetimes, we can express it as the function of a constant, alpha 0, and a term that deals with the effect of the cycling frequency, a term that A2, alpha 2, which deals with the effect of the overstress acceleration, and then a third term which deals with the interaction between the frequency and the overstress and help correct for that. And I would just give you a preview. Later this week in the Academy of Dental Materials meeting, my PhD student, Gaurav Joshi, is going to present a poster. He is poster P6, so please visit his poster and look at the full data set. In addition to what I'm presenting you here, he's looking at R-curve behavior, different surface finishes, different flaw types. There's a lot more information to talk to him about. But just briefly, what we see when we apply the general log linear model to that is that he has looked at the Zerpress, Emax Zerpress material, and he saw when looking at the coefficient for the first term that its 95% confidence interval overlaps 0, and the first term is frequency. So he is not seeing a frequency effect with that material. And with the second term, he sees that the 95% confidence interval does not overlap with 0. It's negative, all in the negative range. And so that tells us the second term, which is related to the overstress condition, has a inverse relationship between stress and lifetime. That's what the negative coefficient indicates. So that's what we expected. And then looking at the coefficient for the third term, it has a confidence interval that overlaps 0 once again. And so for this material, we are not seeing an interaction between frequency and overstress, and we are not seeing a main effect of frequency for this material. Right now we are conducting, Yuan is conducting back home some studies on the Emax Zercad material, where we expect to see a frequency effect and an interaction with the overstress. Okay, so just to summarize, my recommendation for designing accelerated lifetime tests would be to use both the overstress accelerated lifetime testing and the usage rate accelerated lifetime testing. Use those in conjunction, but use the general log linear model to model their interaction and correct for that interaction. And then you be sure to use a finite element analysis to predict the stress distribution that you have in the component, and make sure if you're testing material which can fatigue at some level, that no part of the specimen is exceeding the fatigue limit, because probably in the clinical case we're not exceeding the fatigue limit, and we want to keep it clinically relevant. And then just to remind you, and this is a good segue to Suzanne's presentation, is that you should do fractography on each and every specimen after you test it, to make sure that the failure mode you observe is the same as the one that is observed in clinically retrieved specimens, to make sure that the data you're taking, even though you're taking it faster, you want to make sure that it applies to the clinical case. And I just want to thank the members of my research group. And I cannot do all this by myself, obviously. So I want to thank Baron for testing the endodontically treated teeth. And not shown here is my PhD student, Zara. She returned to Egypt before we took this picture, but she did the finite element modeling on the endodontically treated teeth. You will see Gaurav next week at the Academy of Dental Materials with his Zerpress information. And Pratim was doing the fatigue testing on the implant specimens. And also not pictured here is Jason Vassar, our dental student, who's taking over continuing the project for Pratim. And also like to thank Jay Kumar for fatigue testing of some natural teeth that had metal crowns placed on them. Yuan for running the lab in general, and especially for her finite element modeling skills. John is inventing new equipment and apparatus for us. He designs everything in the laboratory and keeps it running. And especially thank Professora Borba. Is she still here? Yeah? You're not asleep yet? Yeah. Who was a wonderful student for a year and a half in my laboratory, and has now a faculty position in Pasafundo. And although our chief funding is from the NIH, we also received a lot of material donations from the manufacturers and funding from a lot of different government agencies, and so I'm grateful for all of that financial support. So thank you for your attention.